All right, welcome to Lesson 6. This is quite a big moment in your life. We are about to take a look at the fundamental theorem of calculus. There are two parts to it, and we're going to dive into part 1 today. All right, I want to set us up historically before we go into the discovery problem. So we're all familiar with Isaac Newton, one of the founders of calculus. And he had some questions and noticed some things that led him to an incredible discovery. So we've talked about these accumulation functions, which are really just looking at the integral from a to x of f of t dt, and accumulate the area under a curve. And in doing so, Newton, of course, had this idea about looking at the area under a velocity curve. And so he thought of this accumulation function with respect to what if we had a velocity curve here, and what if we went from the initial point, 0, to any point x. Written as we have it right here, where this is looking at the areas between the velocity curve and the t-axis over the first x seconds, so from 0 seconds to x seconds. And what he recognized, of course, we've discussed this, is that this will tell us the net distance that has been traveled, right? You could have some negative velocities, which means your particle will be traveling to the left, and you could have some positive velocities, which would give you some positive areas, so you're traveling to the right. And this he recognized to be a huge component of the position function, right? The only thing that we're missing here is the initial position of your particle. Where does it start off at? And so he thought, okay, well, if I just had some value that represents the initial position, call it c, right? Then what I have here is a function that represents the position of my particle at any time t. And this was a huge discovery, and I want you to just pause for a second. Think about why this is such an incredible result. What's so remarkable is that previously, in the beginning of the year, we looked at position functions, and our goal was to find the instantaneous rate of change. In other words, the velocity. And so that's how we came up with the process of differentiation. And now here, it appears we've come up with a process for reversing that, for taking a velocity function and by a process, getting to a position function. In other words, it seems to say that differentiation and integration are related in some way. And this was something that Newton and Leibniz were able to visualize geometrically and help them to then go ahead and prove what's called the fundamental theorem of calculus, which links the two processes together. So we're going to begin by trying to represent that visually so that we can understand the thought process behind this incredible theorem. Okay, so to discover this relationship, we're going to go ahead and complete this process here. So follow the process, make sure that your graph is graphed neatly and precisely. You don't need to write down all of these steps, but you're going to follow all of them. And you're going to want to write down any key relationships or things that you notice so that if you needed to, you could go back and kind of rework that. And then once you've done so, maybe take a second to sort of let it sink in, and then press play, and we'll discuss it together. Okay, so let's go ahead and look at what we've discovered here. The first thing I've done is I've chosen my arbitrary point x. The red vertical line segments represent the accumulation of area, so that the total area of the red swath is the value of my accumulator function, capital F of x, which of course we find by taking the definite integral of my function lowercase f. Now, I want to take the derivative of capital F. So the definition for a derivative is to take the limit as the change in x approaches 0 of the average rate of change of that function. So the average rate of change of capital F is just going to be the change in f between 2 points divided by the change in x between those 2 points. And we're going to look at that as the change in x between those 2 points approaches 0. So first, we'd like to get a hold of what exactly the change in capital F is. Remember that capital F is the accumulation of area. So the change in capital F is just going to be this next vertical line segment that I'm writing just to the right of my red swath there. Okay? Because that addition or that accumulation of that particular piece is going to be how the value of my accumulation changes right at that instant. It's going to be adding that vertical line segment or the area of that vertical line segment. So let's zoom in on that vertical line segment as I've done over here. The vertical line segment, the width of this vertical line segment is the change in x, right? It's just how much x has changed. the height of this vertical line segment is the value of lowercase f at that particular point, x. So now I have an idea of the dimensions of this vertical line segment, and so the change in capital F is just going to be the area of this vertical line segment. Well, the area of this, if we envision it as this infinitely small rectangle, is going to be the change in x times f of x, which allows me to rewrite my limit statement. Notice now that I can rewrite my numerator. The change in capital F is just going to be the area of this green vertical segment, which is, of course, f of x times delta x. My denominator, of course, is still delta x. And now notice what we can do with the limit. Since we're approaching when delta x is 0, we're never actually getting there, we are free to make the simplification that delta x over delta x is 1. And we're simply evaluating the limit as delta x approaches 0 of f of x. Well, this is a real piece of cake because the value of f of x does not depend on what delta x is, and so we are able to evaluate this limit. It is simply equal to the value of f of x. Now, to truly see what we've just discovered, what we'll need to do is rewrite our original equation, capital F of x, and we're going to take the derivative of both sides with respect to x. In other words, find f prime of x, as we've just written right here. And what we just discovered is that the derivative of capital F of x is equal to lowercase f of x. And just to make things a little more neat, I'm going to write this in shorthand as f prime of x. Right now, you might be wondering why I'm making such a big deal out of this, but I can promise you that this statement that we've just written is one of the more incredible discoveries in mathematics, and its importance and its usefulness is unimaginable at this point. But just by looking at it, we can, in general, see why it might be such a big deal. Notice that what this appears to be saying, and it really is saying this generally, is that if you take the definite integral of a function, in this case lowercase f, and then you take the derivative of it, it has a derivative, first off, and the derivative is in fact just the value, lowercase f of x, which seems to be saying that differentiation and integration kind of do the opposite of one another. They're inverses. And that's basically what it's saying, which is a huge connection. Now we have a way of linking our ability to take derivatives with our ability to take integrals. And we can link the two to make our lives a heck of a lot easier. So this is the fundamental theorem of calculus. It's the first part of the theorem. So let's go ahead and state that now. Okay, the fundamental theorem of calculus, sometimes abbreviated FTC, and it's also known as the fundamental theorem of integral calculus, but oftentimes it's just dropped, the integral is dropped. And this is part 1, which is known as the antiderivative part, and of course will lead us, as you might guess, to part 2. And what it states is this: if f is a continuous function on the closed interval from a to b, then the function capital F of x, which is just the accumulator function, so the integral from a to x of f of t dt. So important to remember what this represents. This function, capital F, has a derivative at every point in x on that closed interval from a to b, and the derivative, df dx, or as we wrote it, f prime of x, which is, of course, the derivative with respect to x of the right side of our equation, that definite integral, is equal to lowercase f evaluated at x. Now, what this says are a couple of really incredible things. The first is that if we have a continuous function, and we look at the accumulator, so our continuous function f, and we look at capital F, which is just the accumulator of the area under this function, lowercase f, that function will always have a derivative at every point. Okay? That's incredibly important to know. And secondly, that we can actually evaluate what that derivative is. It is equivalent to lowercase f evaluated at x, which essentially says if you know what this function is, and you look at the accumulation of the area underneath it, you can find the rate at which that accumulation is changing simply by using your lowercase f. Now, in your notes, I want you to make sure that you leave space underneath this open. We're going to add to this in just a second. But let's go ahead and see how this can help us make things that seem super complicated incredibly simple. All right, let's put it to use. So first, take a look at this expression and take a look back at your theorem and see how you might be able to apply what the theorem states to evaluate or find the value of this expression here. All right, so this is a pretty straightforward application here. Here is the statement of my fundamental theorem of calculus, and so I notice the similarity. This is simply the accumulator function of the area underneath the cosine curve from negative pi to x, and I'm looking at the rate at which that's changing with respect to x, or in other words, taking the derivative of this accumulator function. And so that will be equivalent to the function evaluated at x, in which case this will be equal to cosine x. All right, let's take a look at one more. All right, this looks similar, but notice there is one distinct difference. So take your time with it and recall an important rule of differentiation that will lead you to make sure you get the correct solution. At first glance, this seems like it's very straightforward. The upper limit of integration is different, so we're just going to follow the same rule, but instead of x, I'm going to have x squared. And if you did that, you would be wrong. So if you said cosine of x squared, that's not quite right. Now, to see why, let's notice that this is a composite function, this accumulator function, in that it's exactly the same as our previous function, except that instead of our input being x, our input is x squared. So let's write this out. We have a function y, which is the accumulation from negative pi to u of cosine t dt, and u is equal to x squared. So now if I want to take the derivative of y with respect to x, if I want dy dx, I can do so using the chain rule. I can take the derivative of y with respect to u and the derivative of u with respect to x, and when I multiply those together, I will end up with my desired derivative. So I can take dy du and multiply by du dx. And even though these technically aren't fractions, looking at the chain rule in this way makes it really clear. If I have dy du and I multiply by du dx, that should end up being dy dx, which it is. Now, notice we've already taken the derivative of this with respect to u, right? When we applied the derivative here, we're just implementing the fundamental theorem of calculus that we just discussed, which would be cosine of u. So we have cosine of x squared, so that's this piece here. And now we need du dx, which is just, of course, well, 2x. Which leads us to our final statement. I always like to write that first. 2x cosine x squared. And very briefly, it's helpful to remember why this makes sense conceptually. In our previous problem, our upper limit was x, which meant that every time x changed, our upper limit changed by whatever x changed by, right? Its rate of change was 1, right? And now our upper limit is x squared. So the rate at which x squared changes with respect to x is 2x, which is why we need to account for this in our derivative, right? So we'll take the derivative of cosine, evaluated at this, which is cosine of x squared, but we need to implement the change which occurs to our upper limit when x changes, which is 2x. Okay, so at this point, quickly peel back to where you wrote down the fundamental theorem of calculus. I told you to save some space, and this is why. The chain rule, of course, is something that's often forgotten, and so we want to make sure that we write this down very concretely. If u is a differentiable function of x, then our derivative f prime of x is going to be the derivative with respect to x of our integral from a to u, so we saw when u was x squared. And the way that we evaluate this is we take f of lowercase f of u multiplied by the derivative of u with respect to x, as we just did previously. Make sure you write this down and take a second to be sure you understand how to use it. And then we'll do one more problem together. All right, given this function y, find dy dx. A hint here, go back to your properties of integrals and see if you can notice one that might help you here. So when I look here, I notice that I have a variable in both my limits of integration. And in order to apply the fundamental theorem of calculus, I need to have a constant in my lower limit. So I need to find a way to rewrite this so that I have integrals with a constant in my lower limit. Well, think about 2x and x squared. And then notice that if I took the integral from 0 to x squared, that would encompass everything that I have here, plus a little bit more. The little bit more that I'd have here is the part from 0 to the lower limit. So I can subtract away 0 to 2x. Okay. And this will give me the one that I'm hoping for, which is 2x to x squared. This is just the additivity property, or property number 2, that we discussed a couple lessons ago. So this is what we're going to do, and notice that when I rewrite my integral in this way, I can still take the derivative, and I can take the derivative of a difference separately. So I can take the derivative of each of these separately. So let's go ahead and do that. So that's what I've done right here. I've rewritten my function y in terms of the difference between these two definite integrals. And then I'm taking the derivative of both sides with respect to x. So this will give me dy dx. And I can take the derivative of each of these separately, since it's the derivative of a difference is the difference of the derivatives. And now I can just apply the fundamental theorem of calculus to both of these, being careful to notice that this is an x squared, so a function of x, and this is 2x, which is also a function of x. All right, and now just to make something really clear, I wrote f of t here, and what I'm referring to is the function 1 over 2 plus e to the t, and that was just for convenience, so I didn't have to write for years and years. So now applying the fundamental theorem of calculus, I can take the derivative here, which is just going to be my function 1 over 2 plus e to the t, when t is equal to x squared, times the derivative of x squared, which is just 2x. Then I'm going to subtract the derivative of this definite integral using the fundamental theorem of calculus again to differentiate here. And I will take the derivative of this integral by evaluating f of t at 2x, and then being sure to multiply by the derivative of this upper limit, which is 2. And so I can rewrite my answer as 2x over 2 plus e to the x squared minus 2 over 2 plus e to the 2x. That is dy dx. All right, at this point, go ahead and move on to homework 7.06.